the connection between the parameters and the weather will be much tighter. And if we're not happy with the simulation at that point, it could be that we have to say, well, we have to live with it. It could be that we do all of this and we're not a whole lot further.
But presumably a lot of these errors you put into the models are due to the compensating errors in between the
exactly.
compensations. So if you can do this one right, you could do this one better.
That's the hope. That's why I was saying it kind of disaggregates them. That would be my hope. I haven't shown anything to that effect, but that's kind of the path. So I agree. I don't know who's picking questions. There was one here, one there.
So the run, the time it takes to run these models, it's true that you only need planning for 30 years, but if you want to actually do an equilibrated climate run, you need to equilibrate a coupled ocean, and it takes like 10,000 years.
But is our ocean equilibrated?
Sorry?
Is our ocean equilibrated?
No, but you need...
You want to be close.
But what do you do? I mean, you can't put in a whatever, you can't make up what the ocean equilibrated.
You could assimilate the ocean. I mean, so if you're running the ocean, ocean assimilation is tricky. So one idea is you could, so I'll tell you our thoughts on that. One is you could assimilate the ocean, but our general thought is that what we actually find is that when we run at 2.5 kilometers, the 5 kilometer model looks a lot more like the 2.5 kilometer model than it looks like the 40 kilometer model. So if you back off a factor of 2, you already get 10. So instead of 30 years, you get 300. And even if you go to the 10 kilometers, so using some sort of acceleration techniques by using higher, different resolutions would be the very practical way about going about that. Again, it's not, I don't want to give the impression that, that this is all easy. I'm just saying this is the problem, this is the type of problem as a community that needs to be solved to gain some confidence in the big unknowns.
Yeah, I guess I read the measure that we should, emphasis our improvements on microphysics.
Yeah.
Microphysics is, however, not alone. We have chemistry and biology.
Yeah.
And today we are not in good hands knowing how even aerosols are activated into cloud droplets.
Yeah.
And even less the ice nuclei.
So in this sort of thing, we'll find out if that matters.
Yeah.
So you can make extreme assumptions, and in this, imagine this sort of calculation, or if we do global LES for 2 days, you can say, does it? That's always the particular question, because one of the problems we have now is when we have a small scale process that we don't understand, aerosol activation, we try to see if it's important by putting it in a GCM, but in doing that we sort of short circuit lots of processes. So we kind of let that process project onto the large scale very quickly in a very unnatural way. So an activation scheme suddenly changes a whole field of clouds, where really a difference in an activation scheme just changes that drop and its neighboring drops. And that changes that eddy, and that changes that cloud, and that cloud changes that field. But it has to scale through many scales before it becomes important on a climate scale. And in typical GCMs, we allow these very small scale processes to project, to short circuit all of the weather scales onto the large scale very quickly. And so it's very easy then to get a distorted perspective on how important that is or not. And so what's nice here is this gives us another perspective on whether some of these very small scale uncertainties, whether it's the land surface or it's aerosol in chemistry or biology, how much they project onto the large scale. So I think that will help us understand that. Those processes, we don't know the physics of many of those, and so that's basic research. And so we still have to do that, but then we should do that rather than figuring out how to put it in a large scale model just right, because we might just be compensating the convection scheme, which is compensating the other scheme.
If we don't know the physics, we don't know how sensitive they are to any environmental changes in the source function or whatever. But good job.
Yeah.
And you only change the horizontal resolution.
Vertical too. So I think the vertical is quite important. And one of the things with the Japanese model, they've often run at fairly coarse resolution, and they tend to have problems with ice clouds. And so in these runs, we tend to have sort of order 100 vertical levels. I think it ranges from something like 75 to 140 or something like that levels. And in my experience, when we run idealized large eddy simulation, in the idealized simulations, sometimes the coarse resolution models behave relatively good if you give enough vertical resolution. The vertical resolution seems to be really key because of the stratification in the atmosphere. The other experience that I have from LES is that for a long time now, I've been of the mind that solving the right equations poorly is, this is an example. solving the right equations poorly is often a much better solution than solving the wrong equations well. So this uses the wrong equations, but nominally they're solved well, and this is the right equations, but they're done poorly, they're not resolved, and stuff like that. I tend to favor that if I have a choice. You can give me the right equations and I'll solve them badly, and it tends to behave better than the...
But in this example, they have different vertical.
They have different vertical resolution. This is quite high vertical resolution compared to this. This is very coarse, but yeah, this is different vertical and horizontal. So so what I'm saying there is I'd rather solve the right equations poorly. Means, in some ways I'd rather have more vertical resolution than we actually have in these, and I'd give up some more horizontal resolution for that.
Oh, okay. Go ahead.
Yeah, so I mean, I really like LES and I think it's super important. But so one thing that I think we have learned from the more complex bad models is still the interaction between different compartments of the climate system that we didn't really know they would behave in certain ways, such as the carbon cycle, for example. I think
I'm less carbony, but maybe you could tell me about that. What I'd like to collect is examples where we, maybe we learned something about the carbon cycle that we didn't know before we had a complex model. Or did we actually kind of know that before in the complex model?
No, I think some of the non-linearities in the carbon cycle weren't really.
It'd be good, maybe you can, because I'd be happy to tell, it'd be nice to be able to tell people and why we believe the complex model for that. Because I do remember when I think of carbon, the big things I remember that people talked about were really the land sink. That's always the big thing, where's it going and is it going to come back? The land sink. And it seems like it's still the land sink. Where's it going and is it going to come back?
Oh, that's true, yeah.
And so I could ask, but if you have an example that's specific and you say, actually, because only by having a complex model do we understand that, and we really understand it now.
Maybe we just understood that it's more complex than before. So
Yeah, or there's something that could also be where the complex model showed that the simple model was misleading us. Because I know a lot of the carbon stuff goes back to these barren box models and different things, and so I'm curious, and I'd be happy. It'd be nice to be able to have some examples there.
Maybe this will be the last question, but I guess I was going to ask, when you started off talking about model vanishing and how the additional complexity we've spent a generation developing has not come up with surprises, particularly in shows of simple physics is here, and I can see that this demonstrates a much more trustworthy kind of model coming out of these very high resolution. Do you see any hints that it will give different answers
Yeah, that's
than those simple?
Well, that's where I come back to the tropics. So there's two places where I think it could give different answers, and I just want to know, because for something that's important, it seems like you need another perspective. And one place where I think it could give a different answer is on the sensitivity to small scale things. So one way I like to think about it is in take the aerosol effect, but you could do this for other things, but I understand the aerosol one a bit better, is that if you look at clouds and you have a distribution of clouds, most of your clouds are really thin. So the most frequent cloud, when does a drop become a cloud? Does it have to have a friend or two friends or six friends, or how many friends does a drop need before it gets to be called a cloud? But the most frequent type of cloud, if you would try to segment drops, would be the ones that do nothing. So the most clouds you have do nothing. And the fewest clouds do a ton, and so you have a whole distribution of clouds. In a GCM, we tend to have a caricature of a cloud. It's sort of your average cloud, and so you have my intuition is that this makes the system much more sensitive. Not only do you project onto the large scale much easier, you just project onto the average cloud. So the average cloud has quite right in the middle of the part of the optical depth spectrum where things are important. So if you perturb the average cloud, you get a big effect. If you perturb the most common cloud, you have no effect, because the most common cloud doesn't do anything. And so having this full distribution and looking at its sensitivity, that's on the cloud side, is one. And the other is the tropics. So when you see the tropics, models can do strange things in the tropics. And what I'd like to see is, when we look at the changes in the tropics through the lens of these models, does a different picture emerge? And if not, then I feel a bit better about how we're describing the trajectory of the world into the future. If the picture changes, I'm not one, and don't get me wrong, I don't think just computing everything. It's really, we have to understand why it changes in these models to be confident that, just because we can make nice pictures, that's nicer pictures. I argued at the beginning of the talk that the quality of the model doesn't go with the niceness of the picture, and then at the end of the talk I tried to show you a lot of nice pictures to show that it's a high quality model. So we'd have to understand these new types of models, but I think that the main thing for me is I see them as an independent way, giving a new view on the system. And so in the tropics I'd like to see if the picture changes. And yeah, so whether I expect it could change, but I don't know.
Okay, I think we might have to end there actually. Is that right?
Yeah.
Yeah. Okay, so let's thank Bjorn again.